So if you look after the compare, we would jump, so we need to save the RIP register somewhere in here just before we jump. What we have in our mind is to tell the program in here that jump after the jump instruction in here. We want it to jump at move RX and 60. So in here first we want to store the RIP. We can't access the RIP directly in here, so if I just, for example, say move, I want to store the RIP value in some other register that we are not using. In this lecture I want to save it in R8 register, so I say R8, and if I say RIP you would get an error saying that no symbol has been defined or something like that. Actually, let me just show the result to you. If I say if I just assemble this file in here, you would see that it says symbol RIP undefined, which means that we can directly access the RIP. We should use the relative addressing and use some other instruction called LEA, or load effective address. The difference of LEA with move is because this loads the address instead of content. Actually, maybe in the next lecture I explain the difference between LEA and move, but for now LEA is for saving the address. So I say R8, which is the destination, and for saving the RIP content right now I say rel, which is for relative addressing, and $. $sign means the current RIP address. So I say load the current RIP address inside the R8 register. Then after that we would jump and well so on, but I want to just save it and go to the debugger to see what happens. Also, after we have jumped to the printing, we want after the syscall to say something like this, to say jump, unconditional jump to the value of R8 register. So in here what we have done is first we say the RIP register to be saved in R8, and after we have jumped to the printing and this has been all executed, instead of going for the start and starting executing this instruction, we want to jump to the R8 value, which is the RIP in here. But well, nothing would change because this process would change again, would just repeat again and again, since we haven't passed the JB printing in here. So first I want to show you the result, then go to the debugger and say now what we should do. It's the same thing that we've been doing throughout the course, that we don't take something for granted. We just have the science behind something, and if we need to learn something, we would do it. If we need to implement something, we would do it using our knowledge. So I just save it, hit enter, exit, assemble it, and now link it, hit enter, execute the compare, hit enter, we have hello world. As we predicted before, we go to the file, Control Shift and T. We could even see the reason or have a solution without going to the GDB. How? If we say jump, dump, up jump, up dump, and then -M to go to the Intel format, -D, and then the compare in here, and hit enter. This is the disassembly of the text section. Now if you look, it says that, or actually let me also go to the GDB too. So I say GDB compare, hit enter, break at start, hit enter, run, step I again, we are at 4000 D7, 4000 D7, this is the compare, step I again, 4000 DA, which would be this one. So right now, if you have a look at the register RIP, it's 4000 DA, right? This is the 4000 DA. If I say info register R8, the value is 0. Now LEA rel $, this instruction is going to get executed, right? So I say step I, then have a look at the RIP register. Well, it points to the next instruction, which is 4000 E1 in here, but the important thing is about the R8 register. If I hit enter, we have 4000 DA, which is the address of the last instruction in here. As we predicted, we wanted to save the current RIP. But in order for us to use this function as we explained and print the hello world one time, we don't need this to get repeated, right? So we need to jump after the JB. Now let's have a look how we could do it. If you look, right now we are in here, 4000 DA is the address of RIP, but we want to jump to 1 byte, 2 byte, 3 byte, 4, 5, 6, 7, and then 8 and 9, which is for the JB. We want to jump 4 bytes after 4000, we want to jump 9 bytes after 4000 DA, which would be at 4000 E3, which is to enter the system call. So again, we are at here, these are 7 bytes, second instruction is 2 byte. Because we want to jump in here, we say rel $, which is the current address of the RIP, plus 9. This would make the jump to go 9 bytes after. Therefore, in here, when we jump to R8, it would jump in here. Let us prove that. I say Ctrl O, hit enter, exit. Now assemble it, link it, execute it, and as you see, we have one hello world thing in here. And actually, other than that, I think we have explained an important maybe topic to the relative addressing, which is one kind of the addressing. You might talk about others too. And also we learn how functions are implemented, and you see what I mean in the next lectures when we are using the call and return. But all the functions use exactly the same concept in here. They calculate the length of the current instruction or where we want to jump, and then in here first we jump to where we want to execute. We save the RIP of the specific location. We jump to the function. After we have finished the function, we create an unconditional jump and jump to the stored RIP, and therefore we will exit in here. Let us also have a look at the GDB. So I execute it again, break, start, run, step I, step I, step I. We are at 4000 DA, which is this one, right? 4000 DA. So right now, if we have a look at the RIP register, it tells us we are at 4000 DA. If we have a look at R8, it tells us it's 0. But if I step I and have a look at RIP register, it points to the next instruction, which is a jump. But if we look at R8 register, it points to 4000 E3 in here. So if we look, 4000 E3 is actually this instruction in here. So now it has been saved in the R8 register. If I say step I, the RIP register would be changed to 4000 B0 because of this jump, because we are currently at this instruction. So I say step I, have a look at RIP register. As you see, 4000 B0, and the R8 hasn't been changed in here, 4000 E3. If I step I a couple of more times in here, we print the hello world, 4000 C9. Let us have a look at 4000 C9, which is syscall. So syscall would happen. We are at 4000 CB, which is to jump to the value of R8 register, which would be 4000 E3, and we enter the exit system call. So I say step I, we are at 4000 E3 as we predicted in here, and again step I, we are at 4000 E8, which is this one, and then we go to the exit system call. So step I and the final step I, and the process has exited normally.